Good. We have just talked about mass balances in welding, about how the deposition rate relates to our productivity in having put so much metal in the form of a weld. And I was hinting here and there to efficiencies, right? I talked about the consumable efficiency. At one point, I talked about the metal efficiency, but I was vague. Okay, I'm not vague anymore. Let's talk about this seriously. In addition to those efficiencies, we have many other types. So I decided to put everything called efficiency all together, because very often when we hear the word efficiency, we think we know what we're talking about, but in reality, there are so many efficiencies that very often people think one efficiency is the other. So what do we have? We have a mass efficiency, which we have been discussing briefly. We have an energy efficiency, which we also have discussed briefly when we talked about nominal heat input and actual heat input, because not all the energy of the welding machine goes into the plate. Some of that goes out in the form of the radiation of the arc. We have time efficiencies. Not 100% of the time we're welding, we are in the shop is time in which we're putting metal down. And then there is something called the strength efficiency. We have not talked about strength of welds yet, and we will do that later in future classes. But because it's an efficiency, I wanted to bring it here. And it's something that is seldom discussed, but it's a good concept that matters. Okay. The relevance of efficiencies is that they have an economic impact. To give you an idea, is how much you dispose in the stubs in stick welding eventually affects your bottom line. So some people say you should keep burning the electrode until you burn your fingers. Huh? Some others are kinder to the welders. Has an environmental impact. For example, in Germany, people started to assess manufacturing processes from the point of view of environmental impact and assessing a CO2 footprint to manufacturing operations. So if through all our fantastic calculations of welding, we come up with a given heat input that would means so many joules to be used in making a weld, maybe I needed many more joules from energy to create that weld. And those joules of energy typically mean an equivalent in tons of CO2. So there is a push to be aware as we do manufacturing of the environmental impact and to have machines that are more energy efficient. Quality impact, for example, when we already discussed how heat input affects cooling rate, and how if we have a big heat input, we might have a slow cooling rate. That we discussed. Now, what we just glanced on is that if we talk about the nominal heat input, that might be a larger value than the actual heat input, and the corresponding cooling rates might be also affected. Sometimes it doesn't matter, sometimes it matters. We'll have all that well understood. And also has a safety impact, because if you have a process that has low mass efficiency, that means that you're losing material somewhere, and that material tends to be red hot and can start fires. Mass efficiency. So what do we have? A process with high spatter would have low mass efficiency. MIG, in globular transfer mode, has a lot of spatter, low mass efficiency. That's pretty bad. Spray transfer, high mass efficiency. In short circuit as a standard short circuit, CV short circuit, tends to have high spatter and low mass efficiency. Processes like STT or CMT or RMD or all those that have this very sophisticated way of breaking the bridge between the weld pool and the electrode as they break the short circuit. Those have lower spatter and higher mass efficiency. So what else? When we don't use 100% of the consumable, in the case of stick, the stub is a significant part of the mass balance that we need to account. And I'm talking about mass balance. In reality, what people care about cost, right? And we do not have a unit on cost in this class, which that might be fixed at some point in the future. But we are almost there as we understand how much mass, how many kilograms of electrodes we need to buy for if we want to make so many kilograms of weld. In stick welding, is quite a bit more because of the stub losses. In MIG or flux core wire-based processes, the coil, you cannot run the whole coil through the machine. So you have a loss, typically negligible, right? In the case of flux core, depending the application and depending your company guidelines, I heard that some rolls of wire, if you don't use them during the day, whatever you didn't use during the day, you just trash, right? That sounds incredibly wasteful to me, but flux core can pick up hydrogen. So the risk of leaving a wire overnight that can pick up moisture and then generate welds that have porosity and needs repair, sometimes that cost is higher than just starting a new wire every day. What other mass losses we have? Well, say we're making roots with 6010, and those roots, after you deposit the weld, you tend to grind it. In 6010, the root passes tend to have like a inside the groove, you have quite a convex weld, and you have what is called the wagon tracks. You need to grind them. Wow. Here, thank you, Eddie. Here I have a comment from somebody who knows. And there are companies that throw away like boxes of stick electrodes, probably those would be 7018, that are low hydrogen electrodes. If you put them in the furnace, you can get the moisture away. And there are many parameters for how long and at what temperature you should do that. The Lincoln Procedure Handbook has a section that says how to recover electrodes that have been exposed to moisture. But yeah, very often it's just faster just to trash it and open a new box, right? And time is money. But when we are so inefficient, we might end up paying a price for that, right? Okay, I was talking about grinding. So 6010 roots have these very big kind of undercuts at the toe of the weld. Is a root pass, so we have the whole groove still out there, and those are ground out. And I'm going to share with you some really fun facts about the grinding out 6010 roots. What other mass losses we have? Flux core, stick welding. The fluxes are part of the electrode you bought, right? And so when you buy electrode, you know that some of that you should dispose of because it's going to become slag, right? And that is tabulated in the literature. And also have other losses that are, I'm not certain on this, but if you remember, we talked that during the position in arc welding, that the droplet temperature is of the order of 2500 C in steel and aluminum. That's very close to boiling. And that means that there is a significant amount of metal evaporation that turns into fumes. I've heard numbers quoted as high as 10% of the electrode burning out in the form of fumes. I think that number is way too high. I have not verified it with our own calculations, right? But just to know that not only we lose material in spatter and in slags, but we also lose material when it flies in the form of metal vapors. So mass efficiencies, we have the overall mass efficiency and the instantaneous. This is the equivalence when we talked about deposition rate, when we talked about the mass balance during welding, right? At the moment I'm welding, I have a balance. But if I looked at my whole day, at my whole shift at the shop, I have to account for other things that don't happen instantaneously, but happen like at discrete events. So this is the mass that went into the deposit, right? Like this for the deposit, this is the mass that went into the deposit. This is what the shop is paid for, what went into the deposit. And nobody cares about anything else. Now, this is what you pay for, the shop pays for, the mass of consumables. The shop pays for this, but gets paid for this other thing. And there is a difference. And you better know your difference, right? So, number one, you have the efficiency of your consumable, right? Not everything in the consumable is going to go to the weld. We already discussed, we know that. But in the overall balance, we have two more things. We have the stub efficiency. That means I'm not burning all, this is relevant for the case of the stick electrode especially. I'm not burning the whole electrode. And then I have a grinding efficiency. That means I put all this metal, but I myself, after having put it, I grind it off because I need to clean up my wagon tracks or whatever other defects I might have. Now, we have these three efficiencies applying to the amount of consumables we buy. The consumable efficiency, let's split into two parts. Consumable efficiency is tabulated. I'm going to share with you in this set of slides, and you're going to have it forever, like some values of efficiencies for the consumable. But they are tricky because consumable efficiency is made out of two parts. One is the fraction of the consumable that is metal. In the case of MIG, 100% of the consumable is metal. The same case of the subarc welding. The wire is 100% metal. But it's not the case of stick welding. In stick welding, only a fraction of the consumable is made out of metal. And a significant part is made out of fluxes. Same with flux core, right? What is inside the wire, that is fluxes that once they become slag, will chip it off. But in addition, we have an efficiency that is intrinsic to the metal. For example, if I take out all the slag, not all the metal still goes in. Some goes in the form of spatter. For example, if I get two flux core wires, one is self-shielded and the other is gas-shielded, the wires might have the same amount of flux, right? The ratio between metal and flux, this Fn, would be the same. However, the self-shielded flux core wires, those have a higher spatter. This metal efficiency is lower. And we're going to see that it shows. Funny thing, this Fm here, how much is metal and how much is flux? Companies don't want to tell me. It kills me. Any competitor can figure that out. So in calculations I have shown you last class, or we do in the future, we tend to assume some numbers. I would love to know this better because things would make our predictions, we could be so much better. But you'll see that by understanding this, you can make sense out of company literature much better. let's see some metal transfer efficiencies in MIG or subarc welding. MIG, if we're in short circuit, right, it says about 93% efficiency. And these numbers are not deep science. This is just some guys welding and seeing what stuck and what didn't stick. And this data, I believe, comes from Lincoln, and I will share with you data also from ESA. Short circuit with pure CO2, you would have a little bit lower efficiency, which means higher spatter. And there's no other type of loss in MIG because it's solid wire. We don't need to worry about slags. STT, of course, very conveniently, Lincoln tells us is 98% efficient, right? It means very little spatter, 2% spatter. Probably yes, for sure is better, right? Here we put it as that the spatter went from 6% spatter to 2% spatter. It's an enormous improvement. But yes, it is true. Less spatter. And we saw this when we discussed our unit on metal transfer. And we saw this when we discussed our unit on MIG and we discussed STT. Okay, let's talk about globular transfer. Globular transfer, lots of spatter, right? And here we have a lower value of metal transfer efficiency. These numbers here are the numbers that you use to calculate how much wire you need to buy and to do a cost analysis. The beauty of this is that we understand where these numbers come from now. How about spray? Spray, 98%, of course, right? Like we are having like this kind of beam of molten metal coming into the weld pool. Here it says pulsed MIG, that is free flight transfer, right? And that is comparable to spray transfer in efficiency, in the amount of low spatter. Subarc welding, 99% efficiency. Why? Because most of the spatter is caught by the slag wall, and then the metal spatter rolls down the side back to the weld pool. Metal transfer in this data is from ESA, and I'm not going to repeat it. It's not as finely discriminated as the data from Lincoln, but what you get to see is more or less the same, right? Like if you have MIG with pure CO2 has a relatively low efficiency, and as you increase the amount of argon in your MIG, you increase the efficiency. And this is efficiency of the metal, right? Metal core, look at this. Metal core, very similar to MIG. Very similar to MIG because we still use like an inert gas shielding. We have no fluxes. And what do we see? Yeah, very similar numbers. Very similar numbers, right? This is a process of spray transfer. And if we had higher argon, you see this 93% is on the low end of the metal transfer in free flight in spray transfer. If we had more argon in this mix, chances are these efficiencies will go up. And now, if these efficiencies were to matter, for example, in Japan, the steel is very expensive, we can think, do I want to put more argon in exchange of losing less steel? We don't have a unit on cost, but we can, you can, if you have to do costing, you can start doing these things rationally, saying, hey, what's my balance in money between argon and steel lost? Flux core, look at this. Now it got interesting. For metal core, we have these 90 plus values, right? Here we have an 89%, but it's almost 90 plus. Let's look at flux core. Flux core is low 80s. Yeah, here we have a 90 again. Like I think it's more of an outlier. What's going on? This gas shielded flux core, right? has an amount of fluxes that will not be part of the metal and are chipped off. And that's why the efficiency is lower. I cannot discriminate how much of this lower efficiency is because of fluxes and how much of it is because of spatter of metal. I'm not too sure, but let me show you something, because nobody tells me what the metal fraction is in these electrodes. But let's see. Now let's see self-shielded. And got interesting because the values now start to crack into the 70s. What's the difference here? The amount of flux is more or less the same. The amount of spatter is very not the same. And you see now how in the consumable efficiency, one of the terms, that is the metal fraction, is more or less the same, but you see in action the other part, that is the efficiency of metal transfer, that in this case is lower because of the higher spatter. With these numbers, you can do pretty good calculations of efficiency, and then you can put them into your mass balance and have pretty good calculations of how much of cross-section of your weld, calculations for the cross-section of the weld you want to make. All right, let's go to stick. What do we see? Even lower. Why? Well, sure, fluxes in flux core were inside. Now fluxes in stick welding are outside. And some of these have lots and lots of fluxes, right? And that's what we see. This is 6010, right? A cellulosic, and this one has relatively low, little amount of slag, right? What we see now, we're cracking into some of these into the 60s in the efficiency. The beauty of this is that we started by talking about the different processes. We talked about metal transfer, and now we are talking about how these numbers affect you. Then we talked about the position rate without knowing where the metal goes. Now we're doing a mass balance, and we put this knowledge together to say, I know how much metal I'm putting in place. And only I know how much metal I'm putting in place. I know the role of each variable. I know the role of travel speed. I know the role of wire feed speed. I know the role of what electrode I choose. And I know the role that different consumables might play from the point of view of spatter or amount of flux. We are owning the design, a welding procedure, to the point in which we can now design a welding procedure. Not always we need it. We already discussed, most welds, you just go and weld and the world is good. And when it gets difficult, you get the procedure handbook of arc welding, and then you become better than 90% of engineers, maybe more. But when things get difficult, you know exactly what to do. And this is universal for all alloys. So if you ever have to weld tantalum, you might not have this tabulated data, but you'll know what factors are at play. Here we have data. This data I have here with these yellow tables that comes from ESA. I have a similar table from Lincoln with very similar numbers. Stub efficiency. Stub efficiency is relatively easy. Is how much of the electrode you're going to use divided the whole. So how much of the electrode you're going to burn divided total length of the electrode. That's it. It is that simple, right? And although you have a flux coating on all this part of the electrode and some part of the stub, you don't have a flux coating, we're not going to worry about that. We're just going to say length that is burned divided total length. And because lots of shops use stick welding, they say, you know, this calculation, don't do the calculation. Here's a table for you. If you have this electrode length and you're going to have this stub length that you're going to discard, this is going to be your stub efficiency. By the way, if you take a look, you'll see that that these numbers, right, with depending on the deposition efficiency you have, might end up being quite slow, quite small. This deposition efficiency here, like 70%, is these numbers we were talking about here, the deposition efficiency. So if we multiply the 12 inches minus the 2-inch stub and the 70% efficiency, that's what we get. Okay, grinding efficiency. Look at this. Isn't this awesome? This table was done in a report led by MatE, that is a very well-known welding engineering in this province, and is a close friend and very knowledgeable. So he led this study of efficiencies in welding that was aiming at seeing at building the ground for an argument for using more flux core instead of stick welding. So you're gonna see that all the time are things like comparing 60-10 or 70-18 against MIG or flux core. They measured how many pounds of electrode they had, and then how many pounds of metal ended up in the weld. Right? And then the efficiency is how much is in the weld divided how many electrodes you bought. Okay, in this province, Alberta, what is the efficiency of root passes with 60-10, right? And this is amazing. The efficiency of passes with 60-10. Look at what they put, more or less 0. I'll let you wonder what 0 means. And as you're thinking 0, I'll tell you something more interesting, right? How much electrode was left after you welded? You know what they wrote more or less 0? Because they didn't measure 0. They measured the negative number. So I want to hear, yeah, probably negative. I want to hear people's thought about how you explain to me that if I'm welding with 60-10, I end up with less metal than before. Thoughts? So let me be clear on the question. People welded with 60-10, they did everything they needed to do to have the root ready for the filler passes, and they end up with negative efficiency. Yes, exactly. Well, you seem to have been in this business. The first time I heard this, I was like, how can it be possible? And aren't I putting metal? What happens is that to get out these wagon tracks, clean up the slag, all those things, people grind it. One of the jokes is that people making root passes with 60-10 are more grinders than welders. Now the question to you is, if I'm going to be like taking out more metal that I put in, why would I bother with putting any metal in? Well, and what happens is this. After you put this pass, you have a root pass, you have the two ends of the pipe together, right? And you ground it, and you have been grinding parts of the joint prep, right? Right. There you go, another expert. So Wes is telling us that the root gap is quite small, right? So you don't put that much material, but when you grind, you get out these wagon tracks, you end up taking out quite a bit. You end up with less material than before, but the material is in the right place, right? In any case, I wanted to share this with you because it's an incredible paradox that I find fascinating. How can you make money by putting metal and ending up with less than you had before? When we talk about the fill and cap, here's the comparison between stick welding and flux core or subarc welding. And of course, the numbers don't possibly compare because flux core, metal core, subarc welding are all wire-based processes in which you don't need to stop and change your electrode or come in and do touch up with the grind, right? But these numbers you have here are the numbers that were measured in our province for the type of things we do here and fit into the context of all these theory and formulas and crazy Greek letter symbols we've been discussing. The Greek letters are just because things need a name. And welding is like a novel that has many, many characters, right? Okay, and Wesley is saying something that I didn't know that, but you want to grind up part of the joint prep so the electrode comes in. All right. Well, and here we have a comment about the removing the slag that in 6010 typically is easy to remove, but when you do the root pass, the slag gets trapped at the toe of the weld, the root pass, that is the toe against the face of the bevel. Anyway, very interesting things to learn. All of these things we can put in a all these things we can put it in a context in which we can do engineering. That is what I want the most. Energy efficiency. I want to talk about two energy efficiencies. I have a bullet for 3 here. I'm going to touch on melting efficiency only briefly. Thermal efficiency is how much energy went into the workpiece versus how much energy came out of the welding machine. The main difference is how much was radiated out, right? That in the light of the arc. There's another efficiency that is called the wall plug efficiency. That is how much energy so this wall plug efficiency, the way I wrote it is backward. It's one over the other. No, I flip it. Is how much energy the machine gives me, how much energy comes out of the welding machine divided how much energy I took from the electrical supply, right? For example, in the case of lasers, that's super low. We discussed that when we discussed laser. And melting efficiency is this. In welding, in fusion welding, we need to melt to have a joint. Now, if all I wanted is to melt, I could bring the weld pool to the melting temperature and not one bit more, and the rest of the plate could be at just the original temperature, and that would be perfect. But of course, the weld pool ends up being hotter than melting, and the plate ends up sucking up quite a bit of heat. So melting efficiency is a concept that says of all the energy you actually did put into the plate, how much did you use for melting? So in arc welding, how can we approximate the thermal efficiency? Okay, so everything that went into the plate, for example, the fall voltage on the plate, let's imagine is MIG. If it is MIG, the plate typically is a cathode. So it'd be the cathode type, cathode fall voltage times current, right? That goes in, thank you very much, is in. The wire, we melt the wire tends to be an anode, is anode fall voltage times current, that went into the anode, And then when the droplet falls into the weld pool. In this set of nodes, well, I need to update, but not 100% of the heat of the droplet goes into the weld pool. Why? Because we have some spatter, right? And the spatter that takes away mass takes some energy away with it. But the spatter is not that big. So we can say the energy of the droplet is also part of the weld, right? We have some amount of heat from the arc. We said about 1/3 of the heat of the arc goes into the plate. Fine. But 2/3 of the heat of the arc go randomly, right? That's energy lost, right? And I'm going to show you a numerical problem with numbers in which we can estimate the thermal efficiency of a process. Here you have from a well-known book, a list of estimated efficiencies, thermal efficiencies of welding processes. And you're gonna see that subarc welding, they give it a relatively high efficiency because how much light is coming out of subarc welding in the form of radiation? None when we do it right, because it's all caught by the slag. So they say a range 0.81 to 0.99. Essentially, very little energy is lost. SMA is shielded metal arc welding, is the way the British call it. Stick welding, 0.8. And these numbers, by the way, some people make a specialty of measuring them and nobody agrees. We can only look at general trends. Say 80%. MIG welding, 85%, because we have losses in the losses of radiation, or 80 or something like that. Look at this. TIG welding is much lower. And let's do a calculation here. Let's look at MIG. Let's say that we have a half-inch gap, a half-inch arc length. I put arc gap. Is it arc length? Half an inch arc length. And so the voltage fall at the contact tip is kind of 0.4 volts. This is based on the calculations we have done before, right? Voltage at the stick out, more or less 2 volts. You know, as of last Tuesday, you knew how to calculate all these things very well. The voltage of the arc is more or less 10.2 volts for this arc length. The cathode fall voltage is 13.8 volts. The anode fall voltage is 4.8. So we would account for contact tip that goes into the wire, the energy in the stick out, the cathode fall voltage, anode fall voltage, and voltage of 1/3 of the voltage of the arc. And I divided by all these voltages together, right? Voltage times current gives us power. So I don't need to put the current here because I'll be multiplying and dividing by the current. And guess what I get? We get 78%, pretty much what they are in the range they are predicted. They're predicting for MIG welding. But this calculation we're doing here has an advantage over these tables. Number one, the only one who believes these tables is the guy who wrote them. Everybody else who writes different tables with different numbers. But what few people can do is if you say, if I increase my arc length, how does my welding efficiency change? So I want to ask you a question. If I increase my arc length, do you expect efficiency to be higher or lower in MIG? Lower, good. I have a suggestion for lower. And of course, because if I increase my arc length, that means a higher amount of energy is going to be radiated out and lost, right? But that's these tables here don't say that, but we know it, right? Look, question. Well, not question because we have the answer. Let's do the same for TIG. Let's say we have a 6 millimeter gap. And here we have the anode fall voltage, right? That is the plate. The cathode fall voltage, but the cathode is thermionic, so has a low voltage. And the arc would be 1 volt per millimeter times 6 millimeters would be these 6 volts. So we would have anode full voltage. Oh, by the way, now I'm not melting the electrode, so the energy that was to the electrode in TIG is taken away by the cooling system. So the only energy that actually goes into the plate is the anode full voltage and 1/3 of the arc. But all the energy I spent was the anode full voltage, yes, cathode full voltage that is dissipated into the cooling system, and all the arc voltage. And that gives us kind of 58%. Is it exact? No, but it's a lot better than ignorance. And these numbers are quite close to what these tables tell us. But these numbers come with insight. And I think there is big value in that. Okay. Here you have another table of welding process of efficiencies that are more or less the same numbers we've been discussing. However, there are 2 new numbers. One, electron beam welding, very high. Other, laser beam welding, huge variation or very low. I'd like to hear a guess of why laser beam welding can have such a low thermal efficiency. Reflection, exactly. So not only this is a problem of waste of energy, of need to have a huge laser even for making small welds. Where does that reflection go? Because let me tell you something. The light of the arc can damage you, but you can take 1 second of arc exposure and not dying with certainty. But if a reflection from the laser catches you, yeah, it might catch you in half. So the reflections of lasers are something we need to care very much about. Why could the efficiency be higher? Well, if we have a keyhole, now the light comes in and starts bouncing all in here and tends to get trapped. So in lasers, we have a big difference in absorptivity, in thermal efficiency, whether we have what they call the conduction mode penetration, which is not conduction but convection, but I'm not going to argue with that. But the beam bounces off the molecular reflector of the weld pool, or a high efficiency when you have a keyhole. Electron beam. So interestingly enough, this graph we're showing you about efficiency that is was calculated in our lab. We had a project on electron beam welding, and we needed to know the efficiency. And we learned something really cool. You know what we learned? We know from electron microscopy, we can make images from backscattered electrons. If we have no backscattered electrons, no images. Huh. But if they're backscattered electrons, those electrons that are backscattering are taking energy away with them. And the same happens in electron beam welding. That's quite awesome. So if you, and there are formulas for calculating the amount of backscattered electrons. And if you have heavy elements, the electrons bounce off like a ping pong ball. And if the elements are lighter, the electrons can penetrate and stay there with less backscattered. That's the reason we see the contrast we see in backscattered ACM, right? In electron beam welding, what it means is that for materials like iron, if we're welding in the conduction mode, we could expect something of the order of 78% efficiency based on the backscatter electrons. If we have keyhole penetration, then the efficiency is a lot higher because backscatter electrons would be caught inside the tube of the the keyhole. All right, it is 3:20, so I'd like to stop here. and I'll try to wrap this up quickly. On Tuesday, we'll be discussing formulas for predicting cooling rates, thickness of heat affected zone, solidification times, size of the whirlpool. Quite awesome stuff. Let's stop here, and thank you very much.